Okay, first of all, these aren't labeled. This one is called the reciprocal function. If I can spell it. Reciprocal. Reciprocal parent function. And then the reciprocal squared parent function. And listen, this is going to be structured very much like the polynomial unit. What I mean is, we spent a little bit of time talking about the power functions, like s to the power 4, s to the power 5, and transformations of those parent functions. Now we'll do these two parent functions and transformations of these today and tomorrow. And then next week, we start doing the weirder ones. Uh, so, like polynomials, the parent functions were just nice simple graphs like that, and like that, whereas the real polynomials had weirder graphs. So the same way here. All right, domain excludes what number in both cases? 0. So and we'll use interval notation. If you plug in 0 in both cases, you get undefined, right? So we'll draw the graphs and we'll talk about the range. And let's watch. If you plug in 1 into the first function, it's just 1 over x. So 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third, and so forth. Hold on, I'm going to do some. So it's a half, and a third, and a fourth, and so forth. So as you go out to the right, approaching 0 from above, let's say, getting closer and closer to the y by 0 forever. And then as you go to the left, well, first of all, at negative 1, 1 over negative 1 is negative 1. And negative 2 you get negative 1 half, negative 3 you get negative 1 third. And so it's approaching 0, but from below this one. Okay? And I just want to tell you again, if you try making a table, it's essentially what I was saying, and you only use integers, sometimes it fails you, like it did here. Because then you plug in like a half. If I plug in a half, the reciprocal of a half is 2, I get that point. Plug in a third, I get 3, and so forth. So I only had half the graph so far. The rest of it comes by plugging in fractions. So I can do this. There you go. There's your reciprocal parent function. The range, by the way, includes everything but 0, just like the main did. Then I come over here, and same idea. If I plug in 1, I get 1. If I plug in 2, I get 1 over 4. Plug in 3, I get 1 over 9. So it actually approaches 0 faster. It's quite a different shape. And if I plug in like a half, I get 4. Plug in a third, I get 9. Plug in a fifth, I get 25, and so forth. So it's actually the exact same shape. Of course, overall, it's different because both sides go to infinity. Both sides have positive y values. But I'm saying each branch is also different from over here. Here, the whole thing has symmetry about the line y equals x and has symmetry about the line y equals negative x. This one doesn't, and neither branch has symmetry across either one of those lines. First, this has y-axis symmetry. With the range here, it's a positive, yeah. All right, now let's talk behavior statements. First of all, where it says in behavior, put long run. Those two terms are synonymous. Okay? You have long run and short run behavior. Long run, we talked about this limit as x goes to infinity or negative infinity. Here, so we'll write these as limit statements, LIM, and you put as x goes to infinity, you have to squeeze that in under there. And the limit as x goes to negative infinity. In both cases, you're talking about the limit of the function. Now watch. So for long run behavior, that kind of fails, doesn't it? Let's see, obscure that. Okay. Okay. So I'm saying if you ignore everything else, like I said, you're trying to focus on behavior at infinity. So you can't even see this in the graph, really. So let's say x approaching infinity, you're talking about x being 1,000 and a million and billions and a trillion. Well, your y values will be 1,000th, a millionth, a billionth, a trillion, yes? And so as x increases with that bound, what the y values do, what the function values do, they approach 0, but we say from above. And so you put 0. And if you go in the other direction, towards negative infinity, you can see the y values are going to go from above to 0 forever, but now they're approaching from below. What the negative sign means there. Let's go do the long-run behavior here. And this one's different because they're approaching 0 from above in both directions, right? Now let's talk about short-run behavior. When we talk about short-run behavior, you always mean your behavior of the graph around some specific x value. On these, the asymptotes are at 0. Y equals 0 is the horizontal asymptote. X equals 0 is the vertical asymptote. That's going to change. You know, we're going to shift these things left, right, up, down, so the asymptotes change. They won't always be zeros, okay? There'll be some other number. But I'm saying here, the vertical asymptote is at 0. So that's the only short-run behavior we're going to talk about in this class, is around the vertical asymptotes. You can talk about behavior near any number and calculate you will. But here, like I said, all we care about is vertical asymptotes, which happen at 0 in both cases. So write down the limit as x approaches 0. But the problem is, I need more than that because you get two different behaviors. If you're on the right side of 0, imagine if your x value is like 1,000th, and a millionth, and a billionth, and a trillionth, what y values do you think you'd see? Bigger and bigger and bigger, yes? And so we say as you get x values closer and closer to 0, on the right side, your y value should be approaching infinity. Whereas on the left side, if you're at negative 1,000, 1 millionth, 1 billionth, 1 trillionth, then you'd say, well, what did I just do? The limit in that case, the limit as you approach 0 on that side, is negative infinity. And like I said, we're missing something, and we need to put the exponents, they're not really exponents, but the notation to indicate from the right and from the left. And so if you're approaching from the right side, that's like from the positive side, that's what the plus sign means. So this, here in this context, that means from the right, that means from the left. And then over here, I'm going to move my blinders over there. If you're near 0 on this function, whether you're approaching from the right or from the left, your y values are going to be positive in both cases, yes. So the limit is x approaches 0 from the right, and this needs to be under the limit part of it, secondly. So they're both go to infinity. All right, let's just finish these, the notes on these. The intervals of increase and decrease and constant, once again. First of all, let me say this. On the left side, it's a decreasing function. On the right side, it's a decreasing function, okay? It would be inappropriate to say it's always decreasing, though. You can look at it. The right side's higher, isn't it? And so I'm just saying, when you write the answer to this, you shouldn't put it like we did the domain, where we said, oh, it's decreasing here, union with that. That's one set. You should just say it's decreasing, because it's never increasing. But it's decreasing on the left half of the graph, comma, and then it was decreasing on the other interval. It's just two separate intervals of decrease. It's not a big deal, but definitely that's the proper way to express it with a comma. And of course, it's never constant. It's constant only if you have a part where it's horizontal. You can't be constant at a point. We're talking about intervals. On the other graph, it starts out doing what? Increasing or decreasing? Yeah. And so it's increasing. And once again, you're talking about as you go from left to right. So it's increasing. The way there's increase in this part, there's decrease in that part. So yeah. So they're increasing first and decreasing second, and there we go. And that function, it gets close to being horizontal as you go out, but it's never horizontal. It's never constant. Continuous? No. But what kind of discontinuity? There's removable, jump, and infinite. Infinite, yeah. There's vertical asymptotes involved. There's infinite discontinuity. So very actually, what is continuous or not? I want yes or no, and if it's no, categorize it. Infinite discontinuity. You can abbreviate it like that if you want. Now, for the odd even neither part, discontinuity. That's what type of discontinuity that is. Now, I want you to write down the definitions for even and odd functions. You're supposed to know these definitions for calculus. This one is an even function. You know, two ways. One is because it has y-axis symmetry, right? And it meets this definition. If I ask you, for instance, what is f of negative 2, what is the answer? Look at the equation, 1 over x squared. What do you get? 1 over 4, right? And if you plug in positive 2, don't you also get 1 over 4? So f of negative 2 and f are the same exact value, and they always will be if you plug in opposites in this function. Whereas that one's odd, because it meets the definition of odd, which is that you get exact opposites y values and plug in opposite x values, which means it has origin symmetry, which you can see in the graph. And here, if I do the same example, f of negative 2 is negative 1 half, f of positive 2 is positive 1 half, and those values are not the same, they're exact opposite. And it always will be, which is why it meets the definition of the last one. Okay. Listen to me. The back of this, by the way, that we don't really need that now. Let me just explain these. These little shortcuts are learned in Algebra 2. Talking about the numerator of the degree in the degree of the numerator in of the denominator. If you look at our parent functions, what is the degree of this denominator? 1, and this is degree 2. What is the degree of both numerators? 0. So the parent functions meet the first case. The numerator is lower degree. And in that case, the horizontal asymptote is always the x-axis, y equals 0. And that's what it says. If the numerator has a lower degree than the denominator, like here in this example, is degree 1, which is less than degree 2, then the asymptote is always that. If they match, like in this example, they're both degree 1, they can both be degree 3. Whatever, you take that ratio of these coefficients, and that tells you a horizontal asymptote in that case. And then if the numerator has a higher degree, then you don't even have a horizontal asymptote, it's oblique, the diagonal line, which we will do. We'll draw a graph of oblique asymptotes. But not yet, not today, because right now, today and tomorrow, we're just doing parent functions and transformations of those. And so, if it's in this form, it's just y equals 0, like you saw. That's the horizontal asymptote. Okay, listen. One thing I want you to appreciate is the fact that here, I guess my point is, the limit statements, really, people have a hard time grasping them initially, quite often. And so the thing is, on these, you can draw the graph from what they gave you. They give the equation, you draw the graph, and then you write the limit statement. But then next week, we'll figure out the limit statements and know how to draw the graph from the limit statements, which means you need to figure these limit statements out now, today and tomorrow. Okay? Now, take up the homework packet. I was going to do one of those for you. And by the way, the day 1 part of the homework packet is due tomorrow, which you should have mostly done before you leave, frankly. I'm going to do this one problem and then keep working on it. Line number 3 in the homework packet. Line number 3 in the homework packet. And one thing you need to understand on this first worksheet, and I think on the second one as well, their reciprocal they call f of x, reciprocal squared parent function they call g of x. Okay? So on number 3, they give you this. You're supposed to know that they mean that you're transforming 1 over x. in order of transformations. We'll write 3 and F1, yes. One thing you should be able to do is write the actual equation. This is that equation written in function notation, where really all you can see is the transformations, and you have to realize is this parent is transformed this way. To write the actual equation for the horizontal, you replace x with x minus 3. So your parent gets x minus 3, put it on there in place of x. And then you tack on the plus 1 after that. So that's your actual equation. Okay? Before we draw it and do everything else, just watch for a second. Let's say it's a g of x instead. So let's say the parent you're supposed to be working with is 1 over x squared. Then you do the same thing. You replace x with x minus 3. So that means it looks like this. X minus 3 parentheses squared with plus 1 tacked on there. So that's 1 over x squared with a horizontal shift. You wrote this. That is not a parent function transformed. It's some other rational function. But it's not one of these two cases. Okay, so on this worksheet that'd be wrong, guaranteed. So I'm just saying that's how you go with the 1 over x squared. All right, let's draw this thing. You're shifting right 3 and up 1. So put your new origin there. Now put a little plus sign there. Because the graph doesn't actually go through the origin, does it? And go and draw your new axes. You don't have to draw them, but you're going to have to draw your graph approaching those, so how would you draw them? And listen, most of it has a vertical expansion, which it doesn't. You're always going to go through that point, 1 to the right and 1 above, and just draw your asymptotic behavior. And go to 1 to the left and 1 below, and approach your asymptotic there as well. So you have the graph done. And don't cross those asymptotes while you draw them first. As far as vertical shift, you're shifting 1 over x, which shifted by 3 and up 1. Now, I had this write the actual equation here for 2 reasons. I didn't really need it for the graph. I didn't really draw the graph. But to find the intercepts, I need the actual equation. And listen, I know you can tell the x-intercepts 2 here, but I want to show the algebra because a lot of times it won't be a whole lot. The y-intercept, I'll do it first because it's easier. You just plug in 0 for x, right? -1/3 plus 1, which is 2/3. So 0, 2/3 is our y-intercept, which is what you see in the graph. It approaches, it crosses the y-axis a little below 1, so I'll look at it. And then the x-intercept, you set your equation equal to 1. Equal to it, sorry. Right? And then let's just get to it. I'll move the 1 over, becomes -1. To make it look like a fraction, you can cross multiply it. This way, you get negative x plus 3. So multiply, you get 1. There's other ways to do it, but that works. 3 over exactly divide by -1, flip sign. Make you get 2 like we expected to. And listen, if you can look at the graph and you can see the x-intercept, you do not have to do algebra. I did this time just to demonstrate how to do algebra. A lot of times you have to, but I'm not going to require you to do that. All right.